Welcome to The Explainer. Today, we're diving into a really powerful R package called nmfkc. Now, this is for all you data folks out there who aren't just satisfied with finding patterns in your data, you want to actually explain them. And that's exactly what this package is built for.
So here's our game plan. We'll kick things off with a quick rundown of what NMF even is. Then we'll look at why the standard way of doing it sometimes just isn't enough. After that, we'll bring in our star player, the nmfkc package, and walk through a real example with some Canadian weather data. And finally, we'll check out what else this powerful tool can do.
Okay, first things first. Let's talk about NMF. What in the world is non-negative matrix factorization?
You know, you can think of NMF as kind of like a recipe deconstructor. It takes something complex, let's say a big data set, and it breaks it down into its core ingredients, these basic additive components. So if you've got a ton of documents, NMF can help you find the underlying topics. Or if you've got images, it can find the fundamental parts that make them up. For all of us R users, the math is pretty straightforward. You take your big data matrix, we'll call it Y, and you approximate it as the product of two smaller, simpler matrices, X and B. It's all about finding those hidden building blocks. But here's the thing, standard NMF isn't the whole story. It's a great tool for sure, but it has some pretty big limitations, and that's the problem we really need to solve here. So here's the problem in a nutshell. Standard NMF is a bit like a detective who can tell you what happened, but has no clue why it happened. It's great at finding patterns, but it can't really use other pieces of information, what we call covariates, to explain them. It's kind of operating in a bubble. Plus, it gets stuck when you throw time series data or nonlinear relationships at it, which, let's be honest, is most of the real world. And this, my friends, is where nmfkc comes to the rescue. This is the solution that lets us take NMF to the next level. The magic is all in this one little change to the formula. Instead of just y equals x times b, we now have y as approximately x times theta times a. And that a at the end, that is the game changer. That's our matrix of covariates, our explanatory variables. So now, the patterns that NMF finds aren't just floating in space. They can be directly explained, modeled, and even predicted by other data you already have. We're finally connecting the dots between the what and the why. And the package doesn't just give you the core idea, it gives you a whole Swiss Army knife of functions to work with. Of course, you've got the main nmfkc function, but then you've got these awesome specialized tools. nmfkc.kernel is there to handle those tricky nonlinear relationships. Got time series data? No problem. nmfkc.r has your back. It even has functions to help you pick the best parameters using cross-validation, which just makes your life so much easier. Okay, enough theory. Let's see this thing in action. We're going to walk through a really cool example from the source material, where we'll analyze daily average temperatures across 35 different cities in Canada. So step one, let's just do a plain old NMF, no covariates yet. We're going to ask it to find two basic climate trends. And for all you R folks watching, check out how clean this code is. It's literally just nmfk, you pass it your data y, and you tell it you want two components. That's it, so simple. And what does it find? Well, it spits out these two really distinct climate patterns. The first one is what you might call the cold pattern. It's that classic bell curve, right? Super cold winters and then a clear peak in the summer. The second one is different. It's a milder pattern. It doesn't really mess with the summer temperatures, but look at the winters. It just lifts them up. It's like a moderating force that makes the winters less harsh. Okay, so now we have our two patterns. The next logical step is to see where they show up. And when we map it out, a really obvious geographic story emerges. That super cold pattern? Yeah, that's dominant in the northern inland cities. No surprise there. And the milder winter lifting pattern? That's all happening on the Pacific coast. So, Vancouver, Victoria, you get the idea. But this is just clustering. We can see the pattern, but can we actually model it? Can we make this thing predictive? And that's the million-dollar question, right? What happens if we actually give the model some help? What if we feed it the longitude and latitude of each city as covariates and ask it to use that information to explain these patterns? This is where we bring out the big guns, the nmck.kernel function. Now, we could just throw in latitude and longitude as they are, but that's a bit basic. What this function does is way smarter. It creates what's called a kernel matrix, which is a fancy way of saying it builds a similarity map. It figures out how geographically close every city is to every other city. This lets the model learn a smooth, continuous relationship. Because we know that climate doesn't just change abruptly at a border, right? It shifts and fades across the landscape. And that's exactly what this captures.
And the result? Whoa, just look at the R-squared. We go from about 0.72 with simple location data all the way up to a whopping 0.92 using this kernel method. That's a huge jump in explanatory power. It means our new model is way, way better at explaining the temperature variations we're seeing. But honestly, the numbers don't even do it justice. The visual result is where it gets really cool.
And here it is. This is the payoff. We've gone from just putting 35 cities into buckets to creating a predictive map for the entire country. The model can now tell you the probability of that milder trend showing up at any location, and it's learned the geography perfectly. You can see this intense hotspot of the milder pattern right on the Pacific coast, and then you see it beautifully fade away as you move northeast. This is so much more powerful than where we started.
So we've seen it work for weather, which is awesome. But don't think this is just a one-trick pony. This framework is incredibly versatile.
I mean, just look at the range of applications. You can use it for topic modeling, take a bunch of presidential speeches and track how different themes ebb and flow over time. Or how about image analysis? You can feed it handwritten digits and it'll figure out the archetype for each number, the essential strokes that make a 2 a 2 and an 8 an 8. You can even point it at messy macroeconomic time series data and have it uncover these hidden economic conditions that are driving things like wages and employment. It's the same core idea, just applied to totally different problems.
And you know what's really great about this? It's not some mystical black box algorithm that you just have to trust. As the author points out, this whole model is actually related to classic statistical frameworks, like the growth curve model that's been around since the 60s. So what nmfkc does is it beautifully bridges that gap between cutting-edge machine learning and good old-fashioned established statistics.
Okay, so let's wrap this up. What are the big things you should walk away with? First, it's all about going beyond just the what. Don't just find patterns. Use covariance to explain why they exist. Second, embrace the messiness of the real world. Use kernel methods to capture those complex, non-linear relationships that simpler models just can't see. Third, this thing is a unifier. You can use one single powerful framework for problems that used to require a whole bunch of different tools. Clustering, regression, topic modeling, time series, you name it. And best of all, it's all right there, accessible and ready to go in the R environment that so many of us already use every day. So that really leaves us with one final question to think about. Your data is full of hidden patterns. The real question is, what are the key variables you have that could finally explain them?